Hello, everyone. Our work introduces a software-based countermeasure for cryptographic code against power side channels and fault injection attacks. It's a joint work between Yale and Virginia Tech. So let's get started. Bloom, Luby, Rubinfield introduced random self-reducible properties in their famous BLR paper in 1993. Bloom received a Turing Award shortly after. This and the next 5 slides exemplifies a randomized self-reduction via integer multiplication. And you want to calculate a multiplication operation with a function p, taking a and b as a parameter. And we are going to demonstrate, instead of calculating a and b directly, we can make the calculation with adding some randomness, some noise on it. For example, we can pick two random numbers, R1 and R2, and make a random number by a plus R plus R1 and B plus R2, right? And then we can pick these R1 and R2 from a uniform random distribution and add those to A and B. And this makes this purple area, right? It represents this area. And from this area, we subtract A with the randomness R2, right? Which is A times R2. And we do the same for R1 times B. And then we can subtract the part that we calculate three only random numbers, which is R1 times R2. And we will end up with the actual result, so which is A times B, right? So this geometrically represents the multiplication. In the BLR paper, many RSR properties are introduced, from integer multiplication to modular exponentiation and inverse and so on. And in this work, we successfully demonstrated how RSR properties can be used to safeguard cryptographic code against power side channel attacks and fault injection attacks. And we also evaluated its effectiveness. Let's dive into about our two main insights, which is basically capture the security parameter N and the security parameter C. Here, we have a calculation that we want to make. Let's call this function z. And this function is a times x plus b times y. A and b can be constant. X and y are actually sensitive. So the um, the parameter n and c, through we got this property, actually a linearity property, right? This function is a linear function, and it should, this is, all of the function is bivariate, this univariate function, but the property should be the same. So, and it has, and this is also a randomized self-reduction. Here, C parameter is against power side channel attacker, because it adds noise, or it masks the power consumption by making computation over random shares. And the parameter N, with the majority voting, is against a fault injection attacker through redundancy. If the attacker introduces a fault in one of the computation, they cannot observe the effects in the output, since the code is going to self-correct itself with majority voting. For example, this Z, A, B, and C all should be the same if there is no fault, but if the attacker can induce a fault up to 1, and if our security parameter N is 3, then 2 of 3 should always be correct, and the majority vote should be correct as well. We will talk about these details later. Let's focus on the computation from the lens of a power side channel attacker. The power side channel attacker tried to correlate the power consumption with the data being executed, but if you randomize the data, the power traces will be indistinguishable for any data, if especially if you pick the random numbers from a uniform distribution. So therefore, what we can do is we provide an X for this computation, but we pick a random number and we pick the second random number correlated with the first number and subtract it from X, and so that the X1 share and the X2 share, the summation of these two guys should be equal to X. And we do the same for Y. So therefore, we do one computation from two random shares and do another computation, two random shares. But according to random self-reductions, this partial result, when we sum this partial result, it should equal to the original value that we want to have. So we repeat the same for A as well. As I said, we use we use here the function Z itself to calculate the result Z. Since we call the function two times with random shares, here the C parameter is 2. The second countermeasure is to repeat the process 3 times, n parameter, right? 3 times, so that if one of the computation errors due to the false introduced by the attacker, it can still correct the result using majority voting. We develop extra countermeasure to protect the majority voting itself, which I'm gonna discuss momentarily. But first, let's look at the formal definition of C random self-reducibility. It's important to note that we don't want to calculate f of x directly. We want to calculate f of x through a function, which is basically the right-hand side of the randomized self-reduction, right? Through C number of query functions, fu1 to fuc. And this u1 and uc should be picked according to given value x. And the randomized reduction is to calculate f of x through a function f, which takes x and its query functions, right? And also f, capital F, uppercase F, should be computed asymptotically faster than f, and the UIs are uniformly distributed, although not necessarily independent. So we exactly benefit from these query functions with random A's. For example, for C number of times here, because the security, this is basically the power side, the C secure countermeasure against power side channel attackers, and the task is to introduce like a mask on the actual input X and do the calculation over these random shares. This is a kind of arithmetic masking. So the approach is black box, because if we replace in here, these alpha 1s to alpha c in the random self-reducible property should take these random shares a1 to ac, right? But we need to function f itself. But here, instead of passing this to mathematical function, we are passing to its implementation p, right? And therefore, we can think of this algorithm as a wrapper around the original implementation p, and we are calling the p itself. It takes, but we don't call the p itself with the actual value. We call p with the random shares. So we have a we are able to, we assume we are able to randomly split a given as a given x into random shares. And the countermeasure basically takes the p implementation, and also this line 4 should be replaced with the original random self-reducible property and the C security parameter. So the second countermeasure is insecure countermeasure against fault injection attacks. Is basically this time takes an additional parameter n to collect n number of votes, answer, and execute the C-secure countermeasure n times. One or more results may be faulty, but the majority voting is going to provide the self-consistency. If the majority of the results are correct, then the result should be correct. The number of fault that can be introduced by the attacker cannot be more than n over 2, half of n's, right? So this is by default an assumption. And this shows a so-called C-N secure countermeasure over modular operation, right? It takes the modular R, the modular operation itself, the secret value X, and the C and security parameters, right? So based on the number of C, it creates C number of shares from a given X. We are going to talk about the random split function momentarily. And then we query the original function P with each random shares from X1 to XC with a given field, right? And then we collect the answers with an array, with a list, and then we return the majority of the votes, of the results, sorry. And yeah, and then we can adjust N and C to make it more stronger to fault injection and power side channel attackers. So regarding the number of N, how we can select this N, right? So and in order to make an assumption over the number of ants, we need to have a priors about the attacker's probability of success. And we call this epsilon fault tolerance, which is the probability P of X is not equal to F of X, should be less than epsilon. And therefore, we can bound this n parameter using this formulation. The proof uses chain of bonds to derive this equation for n. The formulation relies on epsilon and the confidence parameter. And although this is the theoretical conservative bound, in practice we achieved good result with smaller n's. And yeah, so basically this N is a prior about the attacker's probability of inject a fault successfully, right? Yeah. So the minimum is like for if we consider N3, then the attacker for each run of the computation can introduce at most one fault or no fault, right? If there's a probability of introducing two-fold, then our countermeasure may not work with some probability. So regarding the random split function, basically it is easy to configure it, right? So it takes C and input X as a parameter, and in a loop, it returns all random splits. Basically, all random numbers less than C, and the final share can be obtained by subtracting the sum of all random shares less than C from the input X, and then we find the last randomness and their summation. In terms of sanity check, their summation should be equal to X. Regarding the majority vote algorithm, we use the Boyer-Morse majority voting algorithm, which is very efficient and clever algorithm that runs O n, and where n is the count of vote. The details are given in the paper. However, a fault can hit a majority vote as well. Therefore, we came up with a randomized reduction for it. And this is the self-corrected version of the majority voting algorithm. We also added a shuffle function against power side-channel attackers. We also added a loop bound check in case the fault causes a skip of the loop. The shuffle function uses pretty efficient Fisher-Yates shuffle. It randomly swaps the votes on the current index. These are all known randomized self-reductions in the literature. Entity is given by a paper, Lipton in late 1990s. I'm gonna touch upon it momentarily. So, but before this is the protected mode operation, two secure protected mode operation because there are two query functions, and this is the three secure counter, three secure protected mode operation. And regarding predicted modular multiplication and exponentiation, for example, for the modular exponentiation, has a multiplication. And this multiplication should be also protected using algorithm 10 here, right? And let's remember, this is algorithm 11, and algorithm 11 calls algorithm 10. Okay, these should be all random numbers. So regarding algorithm 13, which is in the paper, which is two secure entity number theoretic transform. Why number theoretic transform is important? Because in most of the modern PQC schemes, there is a step for polynomial multiplication if it is if uses like especially in Kyber and similar schemes, they uses modular multiplication, polynomial multiplication pretty seriously. And there are quite a number of addition and multiplication and subtraction operations over this implementation of entity. Although the operation is univariate, overall the operation is the operation is multivariate. Overall, the operation is linear. Therefore, follows the linearity property, which is, for example, let's assume our implementation takes fixed number of n's, right? For each input parameter x, we add, we pick a random number and add to that input and make this calculation random, and then we subtract the randomized the entity transformation through the random numbers, and we should obtain the same result. So we evaluate our countermeasures for two end-to-end implementations. One of them is RSA CRT, signature generation algorithm. There are existing attacks for line and line 3. There are modular exponentiation functions. Therefore, we protected them my modular exponentiation countermeasure as known as algorithm 11 that I showed to you. The implementation of modular exponentiation in the cryptographic algorithm actually uses constant time Montgomery ladder, which is a well-known implementation, and we protected that implementation. Regarding another one is we picked the Kybers, which is the NIST standard for public key encryption for TQC schemes, post-quantum cryptographic schemes. And here there was an attack that published last year's chess, which target the polynomial multiplication operation. And the polynomial multiplication operations has been usually done through entity due to their efficiency. And the attack is the entities that calculates S, and this polynomial multiplication is basically key generation part with the A and the C, public key and the secret key S. They are generated, and their multiplication here basically they invalidate S in order to reveal in order to break the operation. Uh, So line 6 represents this location, and it's predicted with algorithm 13 that I showed to you before. To detect, so regarding the evaluation to detect power side channel, like to evaluate power side channel attack, we use TVLA approach, test vector leakage assessment evaluation method. But to detect point of interest, we employ the sum of square pairwise T differences SOST method, setting the threshold at 20% of the maximum. And to detect vulnerabilities, we use TVLA analysis, in which the t-test window is uniformly set to minus plus 8 for all operations. That's our window here, the purple one. As you can see on the figures, all protected operations are within this t-value range. It's an industry standard. They are kept inside the threshold window, whereas unprotected versions shows considerable bias in TVLA results. Regarding the fault injection evaluation, Our experiments yielded three types of outputs: faulty, correct, and board reset in the heat maps. Green indicates instances where all test outputs result in the boarding being reset. This is a this is a probability that you hit an instruction and your fault hit an instruction and turn into an unrecognizable instruction and the machine resets. And the blue signifies the lowest likelihood, which is 0%. So basically, these areas are generating no faults. But the colors closer to red indicate a higher likelihood voltage glitches. So basically, how we arrange is that we start introducing fall with the different start points over the calculation, and we introduce keeping the fault with different durations. So if the duration increases, the probability of hitting a fault also increases, but it concentrated this region for our protected module multiplication operation. But for protected operations, you see almost uh, all faults are green, basically. So this is the same for polynomial multiplication and entity as well, and RSA CRT and Kyber K generation. So with our protection method, we reduce approximately 95.4% of faulty outputs in average, up to 99.4% in modular multiplication. Each call to original function P can be easily parallelized in hardware and vectorized software operations, but we embraces the computation over it due to the security parameters. Masking introduce, for example, the parameter C increases the number of call to function protocol implementation increases, and also N against fault injection also significantly increases the number of operations. So therefore, we introduce significant overhead. However, this can be parallelized to some extent with some special hardware or mixed with special vectorized implementation. And our approach, our approach relies on random self-reductions, um, and this dependency means that our approach may not be universally applicable to all cryptographic operations. And also, we didn't consider the protecting number and the random number generation itself as well. And our future work is to compare our method to masked implementations from power side channel literature, such that we want to compare if there exists a masked entity circuits with our protection, and then compare the latency. And also, we want to investigate the possibility of vectorized and hardware support to cope with the extra latency that our countermeasure introduces. So thank you for your time and attention. I'm happy to answer any questions you might have.